Okay, this is the review that I gave you guys last week. It's 11.3 and 11.4. The first section is all 11.3 stuff. And for the first two problems, it wants us just to classify the pair of events as dependent or independent. So we're going to want to remember what dependent and independent meant. If two events are dependent, that means that the first event will affect the second event. If they're independent, the two events don't have any effect on each other. So so number one, a die is rolled and then it is rolled again. So we're rolling one die and then we're rolling the same die again.
Independent?
They're independent because they're two completely separate rolls. So these are independent events. Number two, on Let's Make a Deal, which was a game show back in the 70s and they brought it back now, the contestant switches doors after a donkey is revealed. So the contestant is switching doors after something else has already happened.
Dependent?
So these are dependent events. Questions 3 and 4, it says that two fair die are tossed. For part A, we need to tell whether the events are inclusive or mutually exclusive by circling one of the choices. And then we need to find the probability of each pair of events as a reduced fraction and as a percent to the nearest 10th. So, for number 3, it says the sum is 10 or the sum is an even number. Remember that when we have an or problem, that's when we're talking about the inclusive and the mutually exclusive. Ands are dependent and independent. And this told you already that it's inclusive or mutually exclusive, so you already knew that, but just for review, pay attention to the ands and the ors. So for this one, remember that our equation for finding inclusive or mutually exclusive probability was the probability of event A plus the probability of event B. And then if it was inclusive, we also had to add the part where it's the probability of A and B. So that'll kind of help us decide. So given the table on the side here, for number 3, we're told that probability for event A, we'll say, is that the sum is 10, and probability of event B, we'll say, is that the sum is an even number. So if we look at our table, all of our options are given right here. So for part A, for event A, we're looking that the sum is 10. So that's going to be anywhere on our table that we have a 10. So that's those 3 spots is where we can have a sum of 10. Now event B is that the sum is an even number. So now we're going to look in our table where we have even numbers. And we have even numbers at all these spots that I'm highlighting in orange. So given what I just highlighted, can we tell if this is inclusive or mutually exclusive? Because remember, an inclusive event is when the two events that we're talking about can happen at the same time, that there's some sort of overlap. And mutually exclusive is when they were completely separate events. So do we know if this is inclusive or mutually exclusive? This is inclusive. And it's inclusive because when the sum is 10, it can also be an even number. 10 is an even number. So these events can happen at the same time. So we're going to use our formula of probability of event A plus probability of event B and subtract the probability of when A and B happen at the same time. So to find the probability of event A, we're going to use our tens that we found. We have 3 tens out of our entire set of possibilities, which is 36. We have 36 different sum possibilities. So we have a 3 over 36 is the probability of event A. We're going to add the probability of event B. So that was every time that we could get an even number, which are highlighted in orange. And there are 18 even numbers out of the 36. So that gives you a probability of 18 out of 36 for event B. And then we have to subtract, because we said it was inclusive, we have to subtract when the probability is A and B. So that's every time that we have a sum of 10 and the sum is an even number. Well, I just said that 10 is always an even number, so that's all 3 of our 10s. So we're going to subtract 3 out of our total, which was 36. That's the probability of A and B. So now we're going to combine these fractions. The 3 out of 36 minus the 3 out of 36 ends up canceling. And we end up with just 18 out of 36. And this wants it wrote as a reduced fraction. So we're going to divide this out. And you end up with 1/2. So 1/2 is your reduced fraction. And then you're going to divide that out, get a decimal, and then convert that decimal to a percentage, which is multiplying by 100, or moving the decimal place to the right 2 places. And you should get 50%.
Is anyone lost on that?
So all of these, you just do that formula?
Mm-hmm.
If it's inclusive, that's saying it could be both of those.
Mm-hmm.
That's when you subtract.
Yes,
Where did you
you
get the
have to
minus
subtract.
3 over 36?
Wait, what?
Where'd you get the minus 3 over 36?
So the
Where'd you get
minus
that
3 over
from?
36 is the probability of A and B. So that's when your sum is 10 and the sum is an even number.
Because every time the sum is 10, it's going to be the even number, so they both.
It's the overlapping.
Yeah, so that's like your overlapping section. So we're going to look at when the sum was 10, was in those 3 spots. And then you also want to know when the sum is an even number. Well, like we said, 10 is always an even number, so all 3 of those are A and B. So that's where the 3 out of 36 came. Okay?
Caitlin, mutually exclusive, the other one is when you can't have, like, if, remember the example, who's 6 foot tall and 7 foot tall? Can someone be 6 foot and 7 foot tall?
No.
No. This is inclusive because you could have a number that's a sum of 10 and it be even. Because there's, it's like saying, can you be 6 foot tall and have brown hair? Yeah, you could be both.
So number 4 is another example of an inclusive or a mutually exclusive. We're given that the first die shows a 1. So when we roll the first die and it shows a number 1, or the sum is greater than 9. So event A, we'll say, is when the first die shows a 1, and event B is when it's greater than 9. So when the first die shows a 1, we can look at it right here. And technically, we can look at this 2 different ways. The first die will show a 1 out of the 6 times, because there are 6 choices on a die. Or, if we're looking at the sums, 1 will occur 6 different times out of our total of 36 times. Because you can have a 1 here with this one, a 1 with the 2, a 1 with the 3, and so on. So you would get, for that, you would get a 6 out of 36, which reduces down to the 1 out of 6. So you can use either one. So our first event is when it shows a 1. Our second event is when the sum is greater than 9. So here we're looking on our chart for all the numbers that are greater than 9. So that's our 10s, our 11s, and our 12. So these are our options for greater than 9. And these were our options for when we roll a 1 with the first die. So are these inclusive or mutually exclusive events? They're mutually exclusive. You can't roll a 1 with the first die and get a sum greater than 9. So when we have a mutually exclusive event, we're not going to have that probability of A and B. So this time we're just going to have probability of A plus probability of B.
And that's it, so you don't minus it.
Nope, because there's no overlap for this one. It's only when it's inclusive that there's that overlap.
So you just like plus 1 6 and 1 6, and that's it.
So we have probability of A is 1 out of 6, like we said. So probability of A is 1 over 6. Probability of B, we have 1, 2, 3, 4, 5, 6 different choices out of our original 36. So then we'll add these and get our reduced fraction. And we get 1/3. So 1/3 is our reduced fraction. And then we want to get that into a percentage again. So we'll switch it to a decimal and then multiply by 100. And we should get 33%. Number 5. Now number 5, we're not told whether it's independent, dependent, mutually exclusive, or inclusive. So we have to decide that for ourselves. So number 5 says, 5A, says what is the probability that the shape is black or has 5 points? So we have that or in the problem, and that or should immediately tell you that we're talking about an inclusive or a mutually exclusive. So you already should have it narrowed down to do those two probabilities. And if you're not sure whether it's inclusive or mutually exclusive, start by finding the probabilities. So we'll say that event A is that the shape is black, and event B is that it has 5 points. So to find the probability of event A, we're going to count all of the black shapes. So we have 1, 2, 3, 4, 5, 6. So we have 6 black shapes, and that's out of 10 is our total set. That's the total number of shapes we have in the circle. So we're going to have 6 out of 10 is our probability for event A. And then we're going to be adding, because we know it's mutually exclusive or inclusive, and those are always adding or subtracting the and part. So our probability for event B, we have to find the probability that it has 5 points. So now we're going to count all of our shapes that have 5 points. So we have 1, 2, 3, 4. 4 shapes with 5 points. And that's again out of our 10 original, or our 10 total shapes. Now, to determine if it's inclusive or mutually exclusive, do we have shapes that are black and have 5 points?
Yeah.
Yeah. So this is going to be an inclusive problem. So we have to subtract that overlap section. So we have 1, 2, 3 shapes that are black and have 5 points. So we have to subtract 3 out of 10 is the probability of A and B. So we're going to combine these fractions. We get 6 plus 4 is 10, minus the 3, so we get 7 over 10. And that fraction is as reduced as it gets. So our fraction is 7 over 10. And then again, we want to get a percentage, so we're going to divide that out and get the decimal, multiply by 100, and you'll get a 70%. Part B. What is the probability of selecting a shape that is black or has 4 points? So again, we have that or, so we know that it's going to be mutually exclusive or inclusive. Event A, we'll say again, is that the shape is black, and event B is that it has 4 points. So the probability of event A is the same as what we had in part A. We still have 6 black shapes out of 10. And then event B now is that it has 4 points. So we have 1, 2, 3, 4 shapes with 4 points. So that's plus 4 out of 10. Now, do we have shapes that are black and have 4 points?
Yeah.
Yes. So this is again an inclusive problem, so we have to subtract the overlap. And we have 1, 2 shapes that are black and have 4 points. So we're subtracting 2 out of 10. Combining these fractions, we have 6 plus 4 is 10, minus the 2 is 8. So we get 8 over 10. That fraction can be reduced to 4 over 5. So your reduced fraction should be 4 out of 5. And again, we're going to switch that to a decimal and get our percentage. And you should get an 80%. On the back, again, we're not told whether these are independent, dependent, mutually exclusive, so we have to decide. So it says, consider a standard deck of cards. One card is taken from the deck and not replaced. And then a second card is selected, and we need to find each probability. So the key word that we're looking at in this one is the and. That's right here in between the two events. We're picking one card and then we're picking another card. So that immediately is going to tell us that we're talking about independent and dependent probabilities. So now we need to decide whether these are independent or dependent probabilities that we're looking at. So when we read the question, we're saying that one card is taken from the deck and not replaced. So we're not replacing that first card that we draw. So is the second draw going to depend on the first draw? If we're not putting that card back? Yeah, so these are going to be dependent events. Because we're not replacing it. That not replacement is very important. These are going to be dependent. So, for part A, we need to find the probability of a spade and then of drawing a spade and then drawing a diamond. So remember that for independent and dependent probability, we take the probability of event A and multiply by the probability of event B. And in this case where we're talking about dependent events, probability of B is going to be dependent on the probability of A. So we will say that event A is drawing the spade and event B is drawing the diamond. So to find the probability of drawing a spade, there are 13 of each suit in a deck of cards. So there are 13 different spades. And that's out of your original 52 cards. So you have a 13 out of 52 chance of drawing a spade. That's your probability for event A. Now we're going to multiply by the probability of event B. Event B is drawing a diamond after we've already drawn a spade. So again, there are 13 of each suit, so there are 13 diamonds. But now, where we've drawn one card out of our deck, we no longer have 52 cards because we've drawn one card out and we're not replacing it. So we have 51 cards left. So you have a 13 out of 51 chance of drawing a diamond. So now you'll multiply these fractions and you should get 13 out of 204, and that'll be your reduced fraction. So 13 over 204 is our reduced fraction. And then again, we're going to divide that out, get a decimal, and make it into our percentage. Our decimal that we get out is approximately 0.064. And we move the decimal place 2 places to the right, or multiply this by 100, and we get 6.4%. For part B, we want to know the probability of drawing an ace and then drawing another ace. So event A is drawing the first ace, event B is drawing the second ace. So to find the probability of event A, we know that there are 4 aces in a standard deck of cards. So you have 4 out of your original 52 for drawing that first ace. And then we're multiplying by the probability of event B, which is drawing a second ace. So we've already drawn one ace in our first draw, and we're not putting that ace back. So we only have 3 aces left if we've already drawn one. And again, since we've drawn one card out, we no longer have 52 cards. We have 51 cards. So on this one, the top and the bottom changed because we're drawing the same thing. So again, you're going to multiply these out. And you're going to get 1 over 221. That's your reduced fraction. When you get a decimal, you're going to get approximately 0.0045, which when you multiply by 100 to get your percentage, you're going to get 0.45%. So there's less than a 5% chance of drawing an ace and then drawing another ace. And then our final section was 11.4. 11.4 dealt with conditional probability. And for 7 through 9, we're dealing with the table that we're given, and we need to find the probabilities as unreduced fractions. So before we start finding our probabilities, when we're given a table, one of the easier ways to help us find these probabilities later is by adding up our rows and our columns. So if we add 128 and 32, that'll give us our total number of middle schoolers. So we end up with 160. If we add the 86 and the 98, that'll give us our total number of high schoolers, which is 184. And then if we add down the columns, so if we add 128 and 86, that'll give us the total number of students that read comic books. So that's 214. And if we add up our novels column, that'll give us the total number of students that read novels. So that's 32 plus 98, which gives us 130. And those numbers are just going to make it easier for us to find our probabilities that we're asked to find in 7 through 9. So anytime you're given a table, it's good to find those totals. So in number 7, we're asked, what is the probability that a student prefers comic books given that the student is in high school? So for conditional probability, it's important that you realize that you're given something. That tells you that it's a conditional probability. You're looking for something, for the probability of something, given something else. And remember, we write these as probability of what we're looking for. So we're looking for the probability that the student prefers comic books. So probability of comic books. Given, remember that our vertical line means given. Given that they're in high school. So that's how we write conditional probability. So for these, we write it as the probability of event A and B divided by the probability of A. Remember that A is the probability that we're given. Event A is what we're given. Event B is what we're looking for. So, for event A, we're interested in the high schoolers. So we want the total number of high schoolers, because remember we have part over the whole. So we have 184 high schoolers. So our bottom number is going to be 184. And then we're interested in, for the top, the probability of A and B. So the probability that they're in high school and they prefer comic books. So high school and comic books is our 86. So we're going to have 86 over 184. And this just asks us to write it as an unreduced fraction, so we can leave it just like that, as 86 over 184. Number 8 asks, what is the probability that a student prefers novels given the student is in middle school? So again, writing our probability, we have probability that they prefer novels given that they're in middle school. So remember, our event B is the novels, our event A is the middle school. So our total number of middle schoolers is 160, because that's our whole row right here was 160. So our bottom number is going to be 160. And we're interested in when the middle schoolers prefer novels. So middle school prefer novels is this 32. So we're going to have 32 over 160. And again, we're writing this as an unreduced fraction, so we can leave it just like that. And then finally, number 9. What is the probability that the student is in middle school given they prefer novels? So you might think that this is the same as number 8, but we're given this time that they prefer novels, and we're looking for those that are in middle school. So this time our probability, we're looking for those in middle school, given that they prefer novels. So this time, novels is our event A, middle school is our event B. So this time when we write out our fraction, our bottom number is going to be our total of people that, or our total of students that read novels. So that's looking at this column. So this time our total is 130. So our bottom number is 130. And then our top number are the middle schoolers that read novels. So again, the 32. So for this one, we have 32 over 130. So they are different probabilities. Does anybody have any questions?
So are those the answers, or is that what you're writing on the line?
Yeah, that's what you're going to write on the line, because it's just asking for unreduced fractions for those answers. And we're done.